time, we, our team, take a breather, and we were tasked with creating a low-cost, long-term ventilation device for low-resource settings. In the US, there are ventilators that treat respiratory distress. However, in low-resource settings, these high-end ventilators are not accessible. Therefore, medical personnel are forced to use this device called the bag valve mask to manually ventilate a patient. However, due to the lack of medical personnel, family members end up having to ventilate loved ones for up to hours on end. This is very inaccurate and tiring. Therefore, there is a need for an automated solution, and that is where we come in.
When designing the device, there were several criteria we had to consider. First, we wanted it to be low cost, since this is for low resource settings. We also wanted to have good control of the breaths per minute and the volume provided, so that we can provide sufficient ventilation. We also wanted to limit size and weight of the device so that it can be portable. Additionally, the device needs to last for a long time, so it can be a proper replacement for the ventilator. And finally, we wanted to limit power usage, since these are low resource settings and power may not always be available. So this is our device, the automated bag valve mask. And now we will go through how the device works.
So the first step in our process is attaching the bag valve mask to our device. So in order to do so, we have a back attachment and a front attachment. So you simply put the bag in, you have to squeeze it a small amount to get it inside the compression, and then you snap the back on like so. You attach it like this, and then the front will slide into one of these 4 holes. So our device is adjustable for all types of bag valve masks. So once you've attached the bag valve mask, you attach this tubing to the bottom, and then this part will go off into the patient's airway. So in order to initiate the compression stroke, you first turn on the device, and it goes through a calibration sequence in which it closes the bag completely and opens it. That will allow the motor to know the full range of motion. We then use the user interface to select the different settings between infant, child, adult, and slow, medium, and fast. So if I want to bag a child at medium, then I would go to child, medium, and then press the white button, which will initiate the compression. And when I want to stop the compression, I hold the white button and let go. And then I can choose a different setting.
In conclusion, our device was able to accomplish all of our design specifications. Our cost was under $120, coming to $117. Our frequency and volume accuracies were all within 10% of our specified values. We were able to supply 100, 250, and 500 milliliters of supplied air for the infant, child, and adult settings, respectively. Our size and weight were also in our requirements. Our size was able to be disassembled to a 9 by 12 by 12 box, and our weight was under 3.6 pounds. In addition, we were able to test our longevity, which we were able to find up to 11 hours of continuous use without any human intervention. And our power usage was also found to be under 11 watts, which allows us to run for a long period of time on a small battery. In our next steps, we plan to create a version 2 of the device and field test it in Thailand. We plan to continue to refine the device and optimize it for a low resource setting, specifically in Thailand, where our sponsor, Dr. Malia, will have the ability to complete field tests as he travels there regularly.